Okay, so some of you are good on reaction types and are ready for another challenge. So there are two types of reactions in terms of the way they feel and some of the things that you observe about them. And those types of reactions are called endothermic and exothermic. And it's all depending on whether or not more energy is exchanged in forming bonds or breaking bonds. So before we go any farther, we're going to go ahead and talk about um, what exactly that means. So, first of all, I want you to imagine that you are in a group of four people, and you are one of these people on the outside of this scenario where you have two people linking arms in the middle. And your goal is to get these two people from interlinking arms and pull them apart. So it takes a lot of energy if they're resisting you to try and pull them towards your side on the outside here. So when you're trying to pull two people apart, it takes a lot of energy out of you in order to break them up. And so I want you to remember the phrase take to break, which means it takes more energy to break bonds than it does to form them. The next thing is, well, what if this is flipped and you are, instead of trying to pull people apart, push them together? So I want you to imagine that you have a person kind of leaning against you, and you push them from leaning against you to pushing them in the middle towards somebody else. So you push them this way. Whoops. You push them this way into the center. So you're basically releasing this dead weight upon you and pushing them towards somebody else. And so when you push two people together, you release this weight off your shoulders. When somebody was leaning up against you, you push them off, and now you don't have to deal with them anymore. And so you're getting two people to actually link arms by pushing them together. And the thing about this is it releases energy in order to form bonds. So when you're forming bonds, you're releasing energy. When you're trying to break them, it's taking energy to do it. Okay? So you release energy to form bonds, you absorb energy in order to break them. Okay? So how are you going to know an exo from an endothermic from a big picture perspective? How does it feel? Okay, so if you can feel heat, or if you can see light or hear sound, you're looking at an exothermic reaction. An amazing example of this is fire. It hits all the bases. So fire is exothermic because you are releasing more energy in order to form bonds on the edge of the plasma. Okay, then on the other hand, if you have something that feels cold, okay, so it's going to feel cold, or if you need heat or light to start a reaction. So if you need to, in order to have the reaction happen, you need to start with fire instead of create fire. Well, then you're probably looking at an endothermic reaction, okay, where energy is being absorbed from the flame in order to cook something, or for example. So what we're going to do is we're going to go down here and do some examples, okay? So if the temperature rises, like in scenario A, when you mix two things together, it's getting hot. If it feels hot to the touch, it's going to be exothermic. If you are burning brightly and releasing heat, okay, light and sound, then you are going to be, again, exothermic. On the flip side, if you're mixing two things together and it gets colder, like baking soda and vinegar does, that's going to be endothermic. And if you need to heat something continually in order to make the reaction happen, you're looking again at endothermic, because that heat has to be absorbed in order to make the reaction happen. So what we're going to do next is learn how to calculate whether or not a reaction is endothermic based on its formula. So here's the first task. We need to look at what we have in the picture. You have copper carbonate, which is CuCO3. Copper is this guy. Carbon is this guy. These are your O's. When the reaction happens, you have Cu, O, and carbon dioxide. What happened? Did we break bonds or did we form them? These guys were already together. These guys were already together. And so what happened was that we split them in the middle to make them separate. And so we broke bonds here. Does it absorb energy to break bonds or does it release to break? And so remember our phrase take to break. It takes energy, it absorbs energy to break bonds. So this decomposition reaction is actually endothermic. If it was flipped and we had a synthesis reaction, that would be exothermic because you're releasing energy in order to form bonds. Okay, now the next step is we have another reaction where it's a little bit more complicated. Okay, we got CH4, 2O2. These are single bonds. Then we got carbon dioxide. And then we got H2O. Okay, so we got these bonds, and we have a combustion reaction here. So the thing is that we need to complete the table to figure out how many bonds are breaking and how many bonds we're forming. Ideally, the number of bonds we're breaking and the bonds we're forming, we can count them. And if we have a greater number of bonds broken or bonds formed, we'll be able to figure out if it's exo or endo. So here's the gist. A single bond will count as one bond. A double bond counts as one bond, and so does a triple. They're just different types of bonds. So here we go. We've got 1, 2, 3, 4 bonds between carbon and hydrogen. So I put 4 bonds. Then between oxygen atoms, I have 1 bond and 2 bonds. So that would be 2 bonds. Then I come down here and I do the same for the other side of the reaction. So on the product side, I have 1 bond, 2 bonds being formed between carbon and oxygen. So that's 2. And then between water, I have 1, 2, 3, 4 between hydrogen and oxygen in H2O. So based on bond counts alone, can we conclude if the reaction is exo or endo? All we got to do is add them. Well, unfortunately, we have 4 plus 2 is 6, and 2 plus 4 is also 6. Neither side is higher, so we can't really conclude based on bond counts whether or not this is an endothermic reaction. So we say no. There is another way that we have to use in order to figure this out. So every bond type in chemistry will have, and when I say bond type, I mean is it between carbon and hydrogen, oxygen and oxygen double bond, etc. For every bond type you have a different energy level. And what we're going to be looking for is comparing the relative energy on each side and seeing which one has a greater change in energy. So here's what we're going to do. First, we need to do some math. So all we got to do is calculate how many CH bonds I have and multiply it by its bond energy value per bond. So I'm going to set up my reaction with an arrow in the middle. I'm going to take care of these two guys on the left side. I'm going to take care of these two guys on the right. So now I'm going to go ahead and get started. I have 4 C to H bonds on the left side. So I need to look at the relative energy for CH. Whoops. And that is going to be 413. So I say 4 bonds times 413. And then I'll get that product. I also need to add it to the other reactant on the left side of the reaction, which is molecular oxygen. So I have 2 oxygen atoms, each having a bond strength of 395 between them. So I have 2 bonds, and so I'm going to say 2 times 395. Then I'm going to carry on to the other side, and I'm going to do the same thing for the product side. So C to O, there are 2 bonds, and your energy level between them is 395. Sorry, 799. Then you add that to how many OH bonds we have, which is 4. And I say 4 times 463. Now it's time to go ahead and calculate the energy levels. So take a moment and do that. First, you should get 1652 for 4 times 413. Then you should get 790 for 2 times 395. Add that to 1652, and you should get a total energy change of 2,442. Then we go to the other side. For 2 times 799, we should get 1598. For 4 times 463, we should get 1852. Just by looking at this, we can tell we're going to have a greater change in energy on the right side. So I'm going to add it, though, just to be sure, and I'm going to get 1852 plus 1598 is equal to 3,450. Now, what does this look like? So, what this means is, for every chemical reaction, you need a certain amount of energy to make it happen. Okay? That's where the arrow is. You need to rise in energy. Your greatest amount of energy in the reaction needs to be at the center. Then you have your reactant side on the left, and you have your product side on the right. So the first thing to do is figure out, well, which side has the greater change in energy from the center. This will drop 2,442. But this will drop lower because it's changing 3,450. So if you have a greater change, remember, this is not the energy level. This is the change in energy from the center of the reaction. If you have a greater change on your right side, this is an exothermic reaction, showing that you have released more energy than you had originally. This is what we started with. This is what we ended with. So this level is what you start with. This level is what you end with. If your ending level has changed more and it has gotten lower than where you started, you have released a net amount of energy, which makes it exothermic. That's fitting because if you look at the formula, this is a combustion reaction. You have O2, you have CO2, and you have H2O, which means you're lighting something on fire. Now on the flip side, well, what would it look like the other way? If you had a greater number on your left, that would mean that from the center of the reaction, you would rise in a greater amount of energy to get to that necessary amount to make the reaction happen, and you would lose less. So if it was flipped, and if you had 3450 on this side and 2442 on this side, that means that your final energy level would be actually higher than where you started, and that would be a net increase in energy, which would be endo. So if we look at a couple examples of curves, we're going to see what that actually means. So for exo and endo, you're just looking at which side is higher. The hump that makes the reaction happen, the necessary energy, is called activation energy. And so that hump is called the activation energy, and if the activation energy, if you have a greater increase, that's endo, because when you release it and it's less of a change than it was on the other side, you're going to end up with a higher amount of energy. So that is going to be an endothermic reaction. Okay? This is the amount of change you had from the beginning level to the end level. What type of reaction would this one be? That's it.